everyone. In this lecture we will be going over an International Mathematics Olympiad problem, namely IMO 1995 problem number 3. Here is a view of this problem. So we would like to determine all integers n strictly greater than 3 such that there are n points in the plane. So these are coplanar points a sub 1, a sub 2, all the way to a sub n, that satisfy simply two conditions simultaneously. So those conditions are that first, no three of these points lie on the same line, so no 3 points are collinear, and second of all, a very bizarre condition, there exist real numbers, n of them actually, such that the area of triangle a sub I, a sub j, a sub k is equal to the sum of the corresponding real numbers p sub I plus p sub j plus p sub k for I, j, and k in these corresponding intervals, I, j, k in increasing order. Obviously we need to show that that this formula works for all such I, j, k's in this range. Okay, so I would like to start with the case n is equal to 4, and so we need to construct a shape such that these sums exist and they would be equal to the area of the respective triangles. Consider simply our 4 points are the vertices of a square. So we have our 4 points a sub 1, a sub 2, a sub 3, and a sub 4. And so those 4 points, and also consider the numbers r sub 1, r sub 2, r sub 3, r sub 4 is equal to 1/6. I claim that r sub I is chosen in the following manner satisfy these conditions, and obviously no 3 points are collinear in this shape. Part A is already satisfied with our current construction. So all we need to do is to confirm the areas of A1, A2, A3, for instance. So the area of say this right triangle here, so we have a unit square, so side lengths 1 each. Obviously the hypotenuse would be √2, and the area of this triangle is obviously 1/2, but at the same time we know that so r1, r2, r3, so these are the ones associated with it. So r1 plus r2 plus r3 is simply 3 times 1/6, which is again 1/2. So in a similar way we can look at the other triangles as well. So obviously there are 4, choose 3 different ways, so 4 different ways to come up with different triangles, but each one will be a right triangle with its side lengths as the sides of a square, so nothing will change. The areas will still be 1/2, and this configuration will actually do the trick. So establishing the case n is equal to 4, so that satisfies, so n is equal to 4 satisfies the conditions, these two conditions given in the problem. Now next we will claim that in the case n is greater than or equal to 5, that's not gonna work. So it's impossible to find such real numbers that satisfy this condition B here. So in order to do that, obviously when you have more than 5 points, you can take a subset, and that subset with 5 points only. So therefore all I will do is I will prove this contradiction that claim that it will not work for n is equal to 5, and then everything above 5 will automatically disqualify as well. So let's have a look at the case n is equal to 5 then. Before I do though, I would like to make the following remark, if you will, or let's call it actually a lemma. that turns out to be the crucial lemma for the rest of this problem. So whenever we are given a quadrilateral a sub I, a sub j, a sub k, a sub l, which is convex actually, this would imply that given our condition B here, Ri plus Rk is equal to Rj plus Rl. So it is actually quite straightforward to prove this result. So let me make a quick note of it here. So the proof will just follow by considering this condition B here. So we just realize that whenever we have a convex quadrilateral like this fashion, AI, AJ, AK, AL, it is possible to split it into two triangles in two different ways. So for instance, the area of the whole quadrilateral, which is let's denote it in this following fashion, obviously, the usual way. It's possible to split it into such like this: a sub I, a sub j, a sub k, plus a sub I, a sub k, a sub l. So that's one representation. Or alternatively, so let's let's write it this one here as well. But alternatively, it's possible also to split it along the following lines: plus a sub j, a sub k, a sub l. So as you can see, I'm splitting my convex quadrilateral in two different ways. But wait, so we know that by definition the area is simply the sum of the respective numbers. Well, obviously, just to clarify, so these p's here in the original problems are the same as my r's here, because I use that notation because there exists a real number, so r stands for real number. Just wanted to clarify. So far, all the r's that I've been using represent those p's actually. But anyhow, so what I will do next is that what is this? So this is associated with r sub I plus r sub j plus r sub k, plus in a similar way the second one will be just r sub I plus r sub k plus r sub l, but then that's obviously equal to r sub I plus r sub j plus r sub l plus r sub j plus r sub k plus r sub l. Let me just drag it slightly down here in order to complete my proof of this lemma. So therefore, obviously, we have quite a few things which just simply cancel out. So obviously the r sub j's vanish, as well as, for instance, r sub i's vanish. We have an r sub k here, they cancel each other out. R sub l goes, and what else? And that's it. So this would simply imply that r sub I plus r sub k is actually equal to r sub j plus r sub l, as we wanted to show. So therefore I will make use of this lemma repeatedly for the rest of the problem. So let me just go ahead and open a new page, and let's show why the case n is equal to 5 is not possible. And therefore, once we establish that, it implies that n is greater or equal to 5 will also not be possible. Therefore, concluding that n is equal to 4 is the only case that works. But okay, so let's start with the case n is equal to 5. Let me open a new page. So therefore, what I have here is that observe that if we have 5 points, so those 5 points, a sub 1, a sub 2, a sub 3, 4, and 5. So, and consider consider these 5 points and the smallest convex polygon containing them. So the smallest convex convex polygon, not necessarily pentagon. So the smallest convex polygon containing these, obviously this polygon containing these points, obviously this polygon will have as its vertices some of these points, maybe all of them, right? So what is the smallest convex polygon containing these points? That we have basically three cases. Either it's a pentagon, or it is a quadrilateral, where one of the points is actually strictly inside the quadrilateral, the fifth point. And finally, it can be a triangle, and two of the points are strictly inside that triangle. So all we will do here is to simply look at these three cases and simply disqualify each of these situations using the lemma that we just produced. So therefore, let's start with the case of a pentagon here. So because the smallest convex polygon containing these points is a pentagon, it's basically the pentagon defined by our 5 points. So we therefore know that this is a convex pentagon, and now we will simply apply our lemma repeatedly. First, let's apply, well, actually in this case we will just apply to two different quadrilaterals. So let's apply, so let's write that down, apply lemma to the following. So let's first apply to quadrilateral a sub 1, a sub 2, a sub 3, a sub 4. That will immediately imply that R1 plus, obviously these two should add up, so R1 plus R3 is equal to R2 plus R4. And in a similar way, I'm going to apply the lemma to the following quadrilateral, A1, A2, A3, A5. In that case, we have that R1 plus R3 is equal to R2 plus R5. But wait a second, combining these two results establishes that R4 is equal to R5. Now, let me open some new space and try to establish why this leads to a contradiction. Now, notice on triangle A sub 1, A sub 2, A sub 4, the area of this triangle is simply R1, R2, R4. Obviously, this is our definition. But wait a second, R4 was simply equal to R5. Therefore, I can replace it with R1 plus R2 plus R5. But again, by definition, this is simply the area of A1, A2, A5. But that by itself establishes that, so these two triangles have equal area. So this immediately implies that obviously A4, A5 is simply parallel to A1, A2. There is no other explanation for these two triangles having the same area, knowing that they share the same base A1, A2. It must be that their heights are equal, and as a result A4, A5 is parallel to A1, A2. But then now also consider the following triangle. Again, applying the definition. Oops, that's an R2, R3 plus R4. And now replacing again the description of R4 with an R5. This establishes that area is also equal to the area of triangle A2, A3, A5. But again, A4, A5 is actually parallel to A2, A3. Now I claim that this gives us the desired contradiction that we need. So the reason is obvious, because we have 2 points, A4 and A5, and then we first have a first set of parallel points, well, parallel line A1, A2, right? So we have a line parallel to that segment. So let's say this is A1 and that's the point A2. In addition, we also know that line A2, A3, or line segment A2, A3 is also parallel to A4, A5. A2 is somewhere here. Let's say A3 is, I don't know, so guess like here. But then this established, because A2 is common in both situations, A1, A2 is the same line as A2, A3, it gives us 3 points on the same line, contradicting the very first condition that no 3 points can be collinear. So therefore we have just proved the first case for the Pentagon. So in a similar way, it's quite easy to also show for the other two. Let's go ahead and I'll just open a new page and establish the same result for the other two cases as well. So let's start with the quadrilateral. So in that case, so we know that our shape, our convex polygon, is the shape of a quadrilateral, and it spans, well, it contains the 4 points, the 5 points, I should say. Therefore, one of the points is actually strictly inside this shape, this quadrilateral, without loss of generality. So let's call it A1, A2, A3, A4. Without loss of generality, let's assume that A5 turns out to be inside triangle A1, A3, A4. As I said, this is without loss of generality. So without loss of generality, A5 is contained inside triangle A1, A3, A4. Let me again remind you, we are in case 2, where the smallest convex polygon containing our 5 points is a quadrilateral. And obviously, because it's the smallest such shapes, our points are 4 of the 5 points describe the vertices of this quadrilateral. So we said this without loss of generality. Now let's apply our lemma again. So let's apply our lemma to the following quadrilaterals. First, let's apply it to quadrilateral A1, A2, A3, A4. This suggests that R1 plus R3 is equal to R2 plus R4, and then I will apply the lemma also to quadrilateral A1, A2, A3, A5, similar to what we did earlier. And from here I'll get that R1 plus R3 is equal to R2 plus R5, again establishing the fact that R4 is equal to R5. Now let's again try to find the contradiction. We claim this is impossible because of the following reason. Notice that R1 plus R3 plus R4 is simply equal to the area of triangle A1, A3, A4, namely this triangle over here. But then obviously this triangle has area greater than A1, A3, A5, because the area of A1, A3, A5, by the picture, because A5 is strictly inside of triangle A1, A3, A4, the area of A1, A3, A5 will be strictly less than A1, A3, A4. And now we can conclude, because R1, this area is simply R1 plus R3 plus R5, and obviously this is a contradiction, because this suggests that R4 is actually strictly greater than, oops, let's just get rid of that equal sign. R4 is strictly greater than R5, a clear contradiction to an earlier finding. So therefore these two findings contradicted, so therefore this configuration is also impossible. Now we have only one configuration left. We have a triangle that's and so three of our points are here, and the remaining 2 points are inside our triangle. So let's say A4 is somewhere here, so let's call it A4, and I claim A5 will be so without loss of generality again. So let's make note of that. So without loss of generality, let A5 be strictly inside triangle A1, A3, A4. So given that, so inside this triangle here, so let me put the triangle sign here. Now, so what we can do again is that we have the following. So consider the area of triangle A1, A2, A3. Well, that is equal to A1, A2, A4, plus, well, obviously A1, A3, A1, A3, A4, and A2, A3, A4, A2, A3, A4. So we have the, so we are basically splitting our triangle into three smaller triangles, but obviously this is equal to, again, applying the definition, plus R1 plus R3 plus R4 plus R2 plus R3 plus R4. Obviously this is this, and so these were the separate groups. But then well, obviously there's an alternative way to make that splitting. It's possible also to split it in the following way. So let me just show you. So we could have also split the shape into like this, these three. So therefore, in that case, let me just come to the result. So we would have gotten that R1 plus R2 plus R5 plus R1 plus R3 plus R5 plus R2 plus R3 plus R5. So that would have been equal to this as well. So those two expressions would have been equal depending on how you partition, if you will, your triangle A1, A2, A3. But again, this would immediately, if these two quantities are basically the same, R1s cancel, R2s cancel, R1s and R3s, R2s and R3s cancel. As a result, we get 3 R4 is equal to 3 R4, R5, or you can say R4 is strictly equal to R5. But that's a contradiction. It kind of contradicts our previous result, which also applies to this condition as well. So for example, you can simply, like we did previously, you can simply consider, for instance, area of triangle A1, A3, A4. Obviously A1, A3, A4, the area here is strictly greater than area A1, A3, A5. But wait a second, so we know that this one here is simply R1 plus R3 plus R5, whereas the left hand side is simply R1 plus R3 plus R4. And again, R1s and R3s are cancelling, suggesting R4 is strictly greater than R5. But again, a contradiction, a clear contradiction here. So therefore, this configuration where the smallest convex polygon spanning those 5 points is a triangle with 2 points inside of our triangle, this configuration also does not work. Therefore, the case n is equal to 5 wouldn't hold, and as such also anything greater than 5 is automatically disqualified as well, because they have a subset with 5 points, which is already disqualified. So that's all this rather lengthy problem. Hope you enjoyed the video. See you in our next lecture.